Thank you very much for coming to this session. I greatly appreciate it. The title of my talk is Network Inference for Monitoring Cyber-Physical Systems. So the outline of the talk is very simple. First, I start with some short motivation of the talk. Then I describe the model that we developed, and then illustrate it in a numerical example, and then talk about the scalability challenges for the model, and then finish with some conclusions and directions for future research. So, as you know, there's been emergence of cyber-physical systems in areas such as power grid and smart grid. Now we have smart meters, and they can connect through the network to the power stations. We also have similar emergence in smart healthcare and specifically telemedicine, where doctors can actually administer decisions remotely. And we also have smart manufacturing. But these are just some of the areas. There are more areas where cyber-physical systems are emerging. And if you look at our life becoming more and more digital, we actually are all little cyber-physical systems nowadays with our smartphones and other gadgets. So this, of course, creates new challenges, and new challenges in terms of systems engineering. An example of the challenge in terms of power grid is now that we have this ability to communicate and get the data from the meters. It creates this problem of when we do the dynamic pricing based on the information from the meters, it creates vulnerabilities in the system which can be exploited through the smart meters and communication networks. In particular, there could be remote meter disconnect attacks, and they can affect the grid stability. In healthcare, there are also some challenges. As you know, many institutions have been introducing electronic medical records, and also the emergence of telemedicine. It really creates the potential for exposure of sensitive private data that we want to protect, and also additional opportunities for insurance fraud. In finance, there is also some specific challenges that are raised by this cyber part of the system. In particular, algorithmic trading has shown that when we use algorithmic trading using supercomputers, it exposes financial markets to artificially created risks. And high-frequency trading was recently shown to increase market volatility. So there's this interesting article by Mao Yi and his co-authors in 2013 that actually talks about the additional exposures that are faced through this high-frequency trading. So now, if you look at the cyber threats, right, the cyber part of the systems is actually creates this exposure to cyber threats. And the cyber threats have been increasing in terms of their complexities. They continue evolving starting from 1980s to nowadays. You can see a dramatic increase in terms of the risks and their complexity. And when before intruder had to have a very high level of knowledge, now even with low technical skills, the attackers can really create a very large damage. So as you can see, right, not only the complexity of cyber threats increase, but also severity in terms of potential consequences, and as well as asymmetry. So about 80% of growth in business-to-consumer markets is actually internet-based. And also, almost all of the business-to-business transactions are electronic. Furthermore, the growth in web-based volume of government business, national infrastructure management, and even our everyday social lives through the networks like LinkedIn and Facebook, right? We are all exposed to those consequences of cyber threats. And furthermore, US is very attractive for the attackers, and the US dominates the list of the countries that are attacked the most often. So when we look at the cloud computing, right, the cloud computing, it's a very convenient model that people really like, because you can outsource your data to cloud service providers, and they can provide you infrastructure as a service, platform as a service, software as a service, or a network as a service, right? So this is a very convenient service. However, providers may have incentive to keep your data secure, or they may not, right? They might have a different incentive, and maybe they want to share, right? Or maybe they are forced to share it, right? As you can see, right, there have been some information, right, in terms of the leaks that some of the providers, right, maybe, you know, leak your data to the government or whatever other, right? This is just one of the examples, right? Everybody remembers the Snowden situation. So now a little joke, right? So you know the situation, current situation. So verify is something that both parties can agree on, right? In 1987, about Soviet Union, Ronald Reagan said, trust but verify. However, right now, the Democrat, right, the Secretary of State John Kerry in 2013, now talking about Russia and Syria, he said verify and verify, right? So now we're transforming from the standard of trust and verify to a new and a more strict standard of verify and verify. So, but verify is definitely something that both Democrats and Republicans can agree on. So the idea is, right, you want to trust your providers, but you want to be able to verify it. So to make the long story short, right, this is our problem. We have a problem of large-scale inference of graphs because the system, we can represent the system as a graph with the nodes represented by computing and storage resources and the arcs as cyber and physical connections. And also have these characteristics, new complex characteristics of these large-scale graphs. The resource and nodes belong to different players or groups, right? They're not all homogeneous. And then some resources or nodes can be monitored and others may not be, right? Because they're not from our group, we will not be able to monitor them. So we have also uncertainty in routing in terms of variability of the movement of the data and information between the resources and nodes, because we have this emergence of cloud-based computing. And is there, right, the main question that arises, is there routing from unsafe or compromised nodes, right? Because if we mainly route through, if our data goes through the safe nodes, we can be safe, right? But we need to verify that there is no additional risks, right? So we might be, we might know about some of the unsafe nodes that we have to deal with, but we want to minimize it, so we want to be aware of whether there is any additional exposures that we are not aware about. So the idea, right, arises of trying to do it statistically and try to infer some of that. So this is actually a complicated problem, and this is the model that we proposed. So the proposed model is basically starts with a connected graph on the nodes, and we have some monitored nodes. So in general, right, we can have a whole subset of, say, the source nodes and the destination nodes, but you know, we start with this simple network, and S and T are monitored nodes. And then we look at the communication between some of the nodes and also some of the actions. And some of that information is available about the network, but some of the information isn't, right? So we need to actually figure out some additional information from what we know, right? So now we also can observe for some of the nodes or some of the pairs of nodes, we can observe communication frequencies. And these are presumed to be known, or some way we are able to estimate them. So we denote them as Pij for every pair of nodes I and j. And then we also have an action, right, on the node. Some of the nodes may be safe and they might create a positive action, or neutral and they might not really change our data. Other nodes might introduce something in the data, or may reduce some sort of the value function, right, and be less beneficial than others, right? Maybe some unsafe nodes. So we assume that the nodes that we monitor is from our group, and they're assumed to be neutral nodes. So basically, the action on that node, right, if we have data X, and then the S nodes and the T nodes, right, the way they act on them, they pretty much don't change the data. So if you look at this, right, the V index V denotes the specific node. So for each action, there is for each node, there is an action. And here's another example, right? An example, for example, we have a node C in V, and it's assumed to be a compromised node. Then the function, the example of the action, right, or the function on that node, it would be, right, 1 minus x, right? For example, we have some byte 1, right? It changes it to the opposite, right? So it changes our information. Or, right, it's a negative action, right? So again, in general, we can come up with much more general functions. And they can even be random functions. So sometimes a node is good node and it's acting with a positive function, and sometimes it creates a negative function for us when it's becoming a compromised node. So again, right, if you look at the communication uncertainty, we know some of the information about the network, but we might not know all the information. And so we might ask ourselves, are there exist some edges about which we don't know, right? Maybe we didn't know before that maybe Google, exposes our data to somebody else. Now, right, and nothing against Google specifically. I'm just making an example. But, right, we want to know whether there's this unknown edge, right? Because maybe some node, let's say node F3, is a compromised node, right, or unsafe node. So we want to know whether 2 can actually route that information to 3, right? So that way, we basically want to infer, right, or check the hypothesis H0 that this edge doesn't belong to our graph. So there is no communication via this unknown edge. Versus alternative that the unknown edge can communicate, right? And in general, you can actually look at subset of edges, right? So not just a single edge, but a subset of those edges. And so now, right, again, coming back to this idea of distributed computing, right, or cloud-based computing, right, the third party handles the data. So there's a variability in terms of how the information can be sent, right? And it depends on what's more efficient in that specific time. And so this variability is modeled as uncertain routing from S to T on this graph or in this graph G. So we could have this pass gamma A, right, the red pass that goes from S to 1, then through the network ends up eventually at n-2, and then from n-2 it ends up in the destination node T. Or our data might travel through this green path, gamma B, which travels from S to 2, then through the network, eventually ends up at n-3, and then goes to T. And in general, we could have this random path, right, that has some number of nodes in between S and T. So this path gamma is a random path from S to T, and this lambda, right, could be a different number of that is more than 0, right? So the data sent multiple times, right? So we want to send data multiple times so we can infer some information, right? This is going to be our information that we're going to base our testing on. So during the ICE transmission or exchange of data or information X, we actually get gamma I, a realization of gamma, right? So when we send it through multiple times, we actually explore different types of gamma. And so some of it might be partially observable. So the idea is when we observe this, right, when what we really observe, right, because we monitor S and T, right, we can observe what we sent from S, and then eventually what we got at T, right? So we observe this Xi. And if you look at the gamma I, right, that's some sort of realization there. I apologize, I should be an index, right? So this I here should be a subscript, and this I is also a subscript. So so again here, right, these are just subscripts there. So what really happens is that you apply the function, right, every time you go through, right, so when we send first through the T1, right, to the node T1I, right, this might change our function, change our data or not, depending on what type of function, right, or action happens at this node T1I. And so on, right, all the way through paths, we basically have this superposition, right, or composition of functions. So now, right, that gives us Xi. So we might not have all that information about which functions it went through, but we do have Xi's. We also have, right, we have uncertainty in routing from S and T. Right now, we can formulate it as a random graph, right? So because we have uncertainty, we can now consider, so the graph G was actually just a regular graph. There wasn't anything random about it. We consider random graph G, and it induces, right? So basically, it's this graph G, this graph gamma is actually a restriction, right? So we have a restriction of the vertices for all possibilities of having this gamma travel from S to T, right? So if it's something that doesn't give us a path from S to T, right, we will not have that vertex in there, right? For example, right, maybe S is connected to some other node, but that node doesn't go anywhere else, right? So obviously we cannot send through that node to the T. So that node wouldn't be included. So basically, right, the V gamma is a restriction of the V. And the same with the edges, right? It's again a restriction of the edges based on the information that we actually able to send information from S to T. So that gives us a random graph. And now also this gamma induces a probability distribution P gamma. And so suppose that there exists a path. So this path gamma 0 from S to T in gamma that actually goes through the edge, right? So we want to know, right, we want to have at least one path that goes through that edge, right, that is a known edge. If we have that, then we actually, right, should get gamma that is different under the hypothesis versus under the H1. And similarly, this induced distribution is also going to be different depending on for H1, H0 or H1. And this can be used, right, this concept can be used to differentiate between our hypothesis versus our alternative. So here's the algorithm, right? So this is a general algorithm, and then I'll illustrate it on an example. So basically, based on the collected data, so this X bar is basically a collected data, right? It's not an average. Sometimes X bar is used to represent an average. This is just collected data on the node T and a destination node. And from that, we can estimate empirical distribution of, right, this X, right, where X is actually whether the information changes. So we want to find whether the information changed, right? Whether any of those actions affected our information. So now we can get this empirical distribution. Also, we can compute, right? So now this is just a computation for H0 based on our knowledge of the graph and also knowledge of the actions and of the nodes, right? So if we know some nodes or some actions of the nodes, we can estimate those functions. And we can also, right, so for example, we can say, okay, we know this node is compromised, right? Or this node is not safe, or undesirable node, we don't want to share the information with, with that person, right? For example, right, in financial, those may be our competitors, right, in financial market. We don't want to share that information with them, so we mark that node as unsafe node, so if the information goes through it, it creates a problem, right? Our function is going to be reduced. So, or it's going to be a negative function, right? So this action would be a negative on that node. And then we have also the PIJs, right? We have those PIJs that are communication frequencies. So knowing all that information actually allows us to estimate distribution, this induced distribution of, right, for any specific value of X, right? Just like we had some empirical distribution, we just computationally estimate this distribution based on H0, right? So H0 is our hypothesis. And then alternative, right? We can also do the same thing for the alternative. Then the key is, after we've done those things, is to compare those distributions. The H0 distribution, induced distribution, versus the H1, right? We compare it to determine whether and when there are sufficient differences between them, right? If we don't have sufficient differences between them, then we can't really choose, right, which one is more likely, right? So we want to have the sufficient difference. If there is a sufficient difference between them, which under some nice conditions there are often sufficient difference between them, then we can use statistical procedure to assess whether the distribution, right, of this H0, right, the induced distribution for X under H0, and the empirical distribution that we got from the data are significantly different. So if they are significantly different, right, then we would reject it. Otherwise, we accept it, right? So in other words, right, if you look at the data that we got and our and our computed distribution, right, P gamma, right, under H0, if it's a good fit for our data that we got, right, then we would accept it. Otherwise, we would reject the hypothesis and instead accept the alternative. Right, so this is just a basic approach. This approach, however, is very computationally intensive if you think about it, and I will illustrate this a little bit later. But before I do that, let me show the example to kind of make it a little more, real, right? So you can see how it works, right? So here's a simple basic example. We have a graph with 4 nodes, and there's a safe node 2 and a compromised node 3. And now our source node is 1, and the sink node is 4, and 1 and 4 are the monitored nodes. So we send the messages from 1 to 4 in G, and then we observe some data on 4. And so another thing that we assume is that we have this estimated probability of being able to route the messages, right? So it's kind of analogous to the PIJs. But in this case, they're all the same for all different connections, right? So if the node exists, let's say 1, 2, we have node 1, 2, we have 2, 4, we have 1, 3, and 3, 4, right? For each of those routes, right, the probability, estimated probability or frequency of them communicating is PE. And we don't really know the unknown connection, but we also assume that it's also going to be PE, right? So this is just a simple example. And this node 3 is a compromised node, so it's going to change the messages. So the question is, can we infer whether compromised node 3 can route messages from or to node 2, right? Because if that happens, right, that's a bad thing for us, right? So we want to know about this node if it does about this arc if it exists, right? So if that edge exists, right, then the data should show that. So we're going to basically infer whether this 2, 3 edge is in our edge set based on the sample data, right? So we sample the data on the node 4, which is our sink node. So now we're actually testing this hypothesis that the edge set is just 1, 3, 2, 4, and 3, 4 against this alternative that not only we have those 4 edges, but we also have this evil edge 2, 3. So now, right, we look at the observations on the node 4, and it's very simple, right? So it's 0 if the message is changed, and it's 1 when the message remains the same. So note that if messages are altered if they are sent via this node 3, right? So for that node, then we look at the function will be 1 minus x. It's not really important, it's just to show how it relates to the general model. So otherwise, our original message is successful reaches 4, and so for F2, the function would be x, right? Again, just to illustrate the model, how it applies to the general model. So now if you look at this, right, we have this 2 different situations. It might be possible that H0 is true, or H1 is true. So first for H0, we can compute this induced probability, right? So basically, the induced probability means, right, that in this case, we're just looking at xi equals to 1, right? Because this is a very simple case, we only need to look at, right, because we have the Bernoulli xi's. So it's either 1 or 0. If we get the 1, then, the opposite is just 1 minus whatever we computed. So now here, right, xi equals 1, what it really says, it says that the message was not altered. It will remain the same. So that means that we went, right, our path was actually, say, 1, 2, 2, 4, right? So that's the only route that doesn't change the message. The alternative route through 3 would change the message. So if we have this, right, this is how we compute the probability, the induced probability. It just basically, this gamma, right, is this, right? And gamma is the route from 1 to 4, right, divided by this. So now we get, if we calculate all of that, right, I'll leave it as an exercise, which you're not going to do, but if you were to do it, right, that's what it comes to, based on our selection of PE, right? So based on that model, it really easily computes to 1/2 for all different i's. And then on the other hand, if we did a similar calculation for H1, when H1 assumption is true, then we have this additional additional situation where this specific probability of gamma being a route from 1 to 4, we have an additional route added. And because of that, what really happens is that this is gonna now be the case, right? So because we had that additional edge between 2 and 3, we have additional routes. And so it's a smaller probability, as you see, right? Because PE is a probability, so it's a positive. It's a smaller chance that it wouldn't, right, it would remain unchanged under H1. And so, right, as long as the PE is non-zero, right, because it could be 0, and in that case, right, they indistinguishable, the H0 and H1, if PE is 0. But that's not a very realistic case, right? If nothing communicates, it's not an interesting case to look at, right? But this is also illustrates, right, of why we compare those P gammas, right, for H1 and H0. So now, based on that, right, we can actually, we can actually let this statistic, and again, right, there is different ways to do the testing, but in this case, right, let's consider this TXB, this random variable representing the number of unchanged messages in n trials. So this is going to be our statistic, and since n trials are Bernoulli, then, right, we can actually get the T that is a binomial. It's binomial distributed variable with this probability parameter. So basically, right, the T is this random variable, so the problem is reduced to testing a hypothesis for binomial parameter pi. Right, so what we're really testing is this. So now, right, because we computed, right, under H0, it's 1/2. Under H1, it's less than 1/2. So now we have to do this one-sided test for the hypothesis H0, P equals 1/2, versus, not P, pi, sorry, pi equals 1/2, versus pi less than 1/2. Does this make sense? And so we can perform this at some selected significance level alpha using, for example, p-value method. And this is just an example of classical test, but the same thing can be done using Bayesian analysis, right? It's just going to have a little different interpretation, but we can look at the Bayesian test as well. So we're looking at this classical test, right? We get the p-value, right? And this is the probability that T is less than Tx, right, where Tx is a value of test statistic for a data sample. And the T is a binomially distributed variable with parameters n and 1/2, right? So n is how many times we send the messages. So now we would reject H0 if p-value is less or equals than alpha, right? If p-value is very small, then it's not likely that the hypothesis is true, so then we have to go with H1. But if p-value is larger than alpha, then we accept H0. So now, right, this is just an example, right? But it could be done in a more general way, right? This is just an example of how we can apply an algorithm for this specific case. But, right, this is a simple case. It's a toy case with only 4 nodes. There are questions, right? There is a question in terms of algorithm scalability, right? If you look at the past, right, the number of paths, what we're really looking, when we're computing those induced probabilities, we're looking at the number of paths, right, or looking through all different paths, and this is how we compute the probabilities. It's based on the all different paths from S to T and G. So the number of the paths from S to T and G, right, it's really important in terms of scalability. It basically determines our scalability. So K depends, right? K depends on number of vertices that we have for the graph, and also the edge density for the graph. And here's this worst case situation, right? It's easy to see if we have a complete graph, then we have a lot of edges and also a lot of paths because of that. And so in the worst case, right, for the complete graph, the density is 1. And we have n vertices, and this is k of n, right, is your number, right, of how many paths we need to explore. So it grows exponentially fast, actually super exponentially. So it's really a very fast growth function in terms of number of nodes. So in the worst case, it becomes very poorly scalable, right? Now let's look at the average case, right? So in the average case, so again, when I'm talking about this, I'm just talking about the blunt force computation, right? The opportunities come when we look at a different, different type of ways to compute graphs. Then we have additional opportunities. But if you just look at the blunt computation, here's our average case. The expected number of paths from S to T in a random graph of size n and density d, right, this is what we have. This is our expected number, right? So we have n minus 2 factorial. Actually, this n should be capital. I apologize for that. This should be capital N. And then again, d to the n minus 1. And then here, right, it can be approximated. There is actually really good, and this is a result by Roberts and Croce from 2007, that this can be approximated. So we can approximate it very nicely with these two functions. So this function, you can recognize this is just a function for the complete graph. Oops. This is function for complete graphs. And then we have this delta function, right, that is used right here, right, of n and the density d, right? And this is this function here. So it actually approximates very nicely this average. But if you look at this, right, it's not so easy. It really depends on the density, on edge density of how large it grows. So notice, right, if the size is n, here's a 50 and 60, right? So it's an increase in 10. But this is a 7, right, the density higher, and this is a lower density. Right, so you actually get, right, when you get a higher density, right, you get so much more than even with more, right, the size is larger, but the density much lower. So it really does depend on density, what we get. And then it's the same thing you can compare again for 70 and 80, right? This is the high density, this is the lower, and this is what it gets. So from that, we can say that it really does depend on the density of how bad the scalability gets. Again, right, this is just for blunt force algorithms. There's improvements when you look at additional approaches, right? So here's the conclusion. We have proposed an interesting methodology for monitoring security of cyber-physical systems, and we demonstrated how to apply our approach and illustrated numerically some of the challenges in scalability, right, that arises when we just use a blunt force computations. And then the current and future research actually addresses these scalability challenges because there is ways to improve. So I'd like to acknowledge that this research was supported by a fellowship from the New Frontiers Institute. I greatly acknowledge this fellowship. That was very helpful. And thank you very much for your patience. There's a lot of technical detail. Any questions?